Good morning, friends. I am S. Selvaraju, working as Associate Professor in the Department of Electronics and Communication Engineering. Today's lecture, we will see how can we derive the electromagnetic wave equation in free space. To obtain the electric and magnetic wave equations, we need to consider the Maxwell's equations. These equations are available in two forms, which are differential and integral form. To derive the electromagnetic wave equation, we are going to prepare the differential equation. Since the fields are going to be changed with respect to the distance as well as time due to the propagation of electromagnetic waves in any medium, whether it is conducting medium or non-conducting medium, that is dielectric medium. So first we will consider the general form of Maxwell's equation, which are given in a differential form as well as integral form. Here we are considering a differential form to derive the wave equations. So since we are going to look at the differential form which is given in the left side in a dot product and cross product. Dot product is given or stands for divergence. So first two equations belongs to the divergence operation, which is given as del dot E. Del dot E which is equal to rho divided by epsilon naught. Another is del dot B, which is equal to 0. So where epsilon naught and rho, these are all constants. E is a electric error. Similarly, we are having a cross product, which is a curve operation given as del cross C is equal to minus dou B by dou T, and del cross B is equal to mu naught J plus mu naught into epsilon naught into dou E by dou T. Here also mu naught and epsilon naught are constants. So first thing we will see what does the parameters which are given in the equation is representing. The major factors E and B, where B is a magnetic flux, which is given in the second equation, which is also equal to mu into H. So H, E are fields. H is a magnetic field, E is an electric field. Why we are considering field? What medium we are going to consider a field? In a free space, unlike the circuits, in a circuit, we are considering a voltage as well as current, which is going to be used for calculating or estimating the power at the destination or for circuit analysis. But in a free space, the voltage and current cannot be measured since there is no physical components existing in a free space. But using a transducer like antenna, we can sense these parameters at a point. So we can measure voltage at a point, that's called electric field. Similarly, current at a point is a magnetic field H. So a B is connected with the H, that is B is magnetic flux. It is equal to mu into H. It will be reflected in the next slide. Similarly, the del. Del means changes. So since it is a free space, the changes is happening at every point. Since it is a free space, every point, unlike a circuit, along the some component or across two components in a circuit, we can find the changes. But here, it is happening at every point in a free space. So electromagnetic waves is existing at every point. Like if you are using a mobile, so you can move the mobile from one point to another point at the boundary of any tower. The signal strength is varying. So at that point, what is energy is existing, that is detected by particular mobile. So that's why the fields are changing in a free space with respect to distance. So the change of fields in three coordinates. So normally the signals are represented minimum two coordinates. What will be changed in this magnitude with respect to time or with respect to distance? But here the signals are or fields are changing in a free space in any place. That's why minimum we are going to consider three coordinates, specifically spherical coordinates. It's x, y, and z. Three coordinates. So the three coordinates are perpendicular to each other. So that is del represents dou by dou x, dou by dou y, dou by dou z. So you can say the first, for an example, if you say del cross E, that means dou E by dou x plus dou E by dou y plus dou Ez divided by dou Z. That is, it indicates the change of electric field in x coordinate, in y coordinate, and z coordinate. As well as the electric field is represented or magnetic field is represented in a bold letter. That means the electric field in x coordinate, electric field in y coordinate, and electric field in z coordinate. Similarly, magnetic Hx, Hy, and Hz. So del means the change of particular field, whether it is electric field or magnetic. It's why it comes under differential form. So we have seen what is electric field, what is magnetic field, why we are considering a field at a point. Since if you want to find the power at any point due to the propagation of signals after 1 kilometer, after 2 kilometer, or after 3 kilometers, or any distance, if you are finding power as we are calculating in the circuit, here in this medium, if you are transmitting a signal from one end, After certain distance, you can calculate what will be change of this power at the another end, far end. So where we require voltage and current, that's why I say here voltage and current may not be measured, but voltage and current at a point we can measure, that's electric field and magnetic field. So that's why the power can be estimated with help of E cross H. That's a power, E cross H. Like we are calculating the power in a circuit V into I, here E cross H. E is connected with voltage, H is connected with current. So similarly, another parameters J is given in the fourth equation is a current density. And similarly, the first two equations states del dot E is equal to some constant rho current intensity, del dot D is equal to 0, that is for static field. So static field, there will not be change, there is in the flux or electric field. That concept we are going to apply later. So now we are going to see how can we derive the wave equation using the differential form of Maxwell's. So this is another form of representation, del dot epsilon E is equal to rho, del dot mu in H is equal to 0. So epsilon is a permittivity. This is used for medium, how far this medium is reacting against the flow of electric field. Similarly, mu is a permeability, this how far it is permitting the magnetic field in your free space. Free space, let's say any medium, not only for free space. If it is free space, they are putting the suffix not, epsilon not and mu not. So the permittivity and permeability will be varying with respect to the type of medium. So another two more equations, del cross E is equal to minus mu dou H by dou T. That already it's given as minus dou B by dou T in the previous slide. That B has been exchanged by mu into H. So mu is taken out since it's a constant. H is only subjected under differentiation. That is minus mu dou H by dou T. Another equation is del cross H is equal to J, that also earlier we have seen, and current density which is equal to sigma into E, conductivity in electric field, plus epsilon into dou E by dou T. So this is another form of differential form of Maxwell's equation. So now we are applying these Maxwell's equations to find the wave equation. So for which we are going to take one more kernel operation, I mean cross product. So we let it del cross E is equal to minus dou B by dou T, where B is equal to mu into H. So taking the curl on both sides, so that's why left side becomes del cross E. The right side is del cross into minus of dou B by dou T. So since why we go for curl, we are mapping this equation. So once if you have del in equation, which stands for differential, different change of the fields. So it is now in first order moment, first order equation. By taking the curl once again for del cross E, that will become second order equation. The second order differential equation is giving a solution for velocity of equations, velocity of waves. That's called wave equation. That's why we are going for one more curl. I mean to make it this single first order equation or single movement to second order equation. Also, the left side we are keeping as it is, del cross E is equal to minus dou by dou t into del cross B. Since B is subjected for variable, it will be changed in this medium. B is changed with respect to x coordinate, y coordinate and z coordinate. Also with respect to time. That's why del is taken inside the B. So the right side becomes minus dou by dou t into del cross B. We are seeing here, so that del cross E results in minus del squared E. This is how minus on both sides, then it will become plus. So del squared E is equal to mu naught epsilon naught dou squared E by dou t square. So if you are taking a single side, you will have del squared E minus mu naught epsilon naught dou squared E by dou t square. That is electric wave equation. Same way here, the magnetic wave equation is del squared B minus mu naught epsilon naught dou squared B by dou t square is equal to 0, where C is equal to 1 by square root of mu naught into epsilon naught, where C is light velocity, that is electromagnetic wave velocity. So that is a procedure. How can we derive the electric and magnetic wave equations from Maxwell's equation, the differential form of Maxwell's equation? So first of all, we are considering the Maxwell's equations in a curl form del cross E and del cross H or del cross B. Then you are taking a curl for del cross E or del cross H according to the types of wave equations which we are going to derive. So that is to become second order equations. Then you are applying identity equation for del cross E or del cross H. That is, if it is del cross E, that identity equation is del into del dot E minus del square E. Where del dot E you are keeping a 0 and the remaining parameters in the left side is minus del square E. So that is a final equation. You have del squared E or del squared H in the left side. The right side is mu naught epsilon naught dou squared E by dou t square or dou squared B by dou t square. So that is equal to 0. So that is steps which are involved to find electric or magnetic wave equations. Thank you.